Hello grade 11 GED 2019-2020 students. We are in third topic, oscillations. Lesson 3.1 as mentioned in your syllabus, simple harmonic motion. This is the first lesson in simple harmonic motion. Our objectives are to describe simple examples of free oscillations, to understand and use the terms amplitude, time period, frequency, angular frequency, and phase difference, to describe simple harmonic motion in terms of displacement and acceleration. An object oscillates when it moves back and forth repeatedly or on either side or of some equilibrium position. This is very important keyword, equilibrium position. If we stop the object from oscillating, it returns back to the equilibrium position, like when we have a simple pendulum. Here the mass will swing, going and coming around this position, and when it stops, it comes back to the same position, this position, which called equilibrium position. So we have free oscillations and forced oscillations. As a free oscillation, the vibration of a guitar string. When you plug a string of a guitar, it gives you some tones or notes depending on the natural frequency of the strings. So also the movement of the pendulum is a free oscillation or the vibration of a quartz crystal. Some oscillations are forced oscillations, like when you are sitting in a bus and the vibration from the engine of the bus transmit to your body, so your body is not vibrating in its own natural frequency, it's vibrating with the frequency of the engine of the bus. Simple harmonic motion as an example of free oscillation. We have so many situations for that. For here, we are only going to talk about long pendulum and mass spring system. Here, for example, there is a string hanging from a ceiling with a mass at the fixed end. At the end, pulling the mass, some distance, will cause swinging the mass to forth and back about this equilibrium position. Also, for a trolley here attached with springs between two clamps, when this trolley is displaced, for example, this is the equilibrium position, when it is displaced certain distance here, it will start oscillating back and forth along the bench around this equilibrium position. And the same when we have a mass spring system, spring attached with a mass, this is the equilibrium position. When pulling it a distance here, it will start bouncing. This mass will come up and down over this equilibrium position, and when it stops, it will be back to the same position. Now we have here for an oscillation to be simple harmonic motion, we have requirements. A mass of the oscillation, this is a mass, okay, this is the mass here, this is a position where the mass is in equilibrium, as we have seen. This is the equilibrium position for the pendulum. This is the equilibrium position for the mass spring system. There should be, this is a very important keyword, restoring force that acts to return the mass to its equilibrium position. Now, when the mass is here or the other side, there is a restoring force which always try to bring the mass back to its equilibrium position. Also here, if it is down, the equilibrium, the force will act up towards the equilibrium position to return the mass back, when it is up here, the force will act here toward the equilibrium position to return the mass back to its equilibrium position. The restoring force is directly proportional to the displacement of the mass from its equilibrium position and direct toward that point. What do we mean by that? Now, first of all, we have to know, for example, for a mass, for a pendulum, this is the equilibrium point, position, sorry, and the mass can be here. It can be anywhere here. Yeah, the distance from the equilibrium point to the position of the mass, wherever the mass is called displacement, x. It is a vector quantity. It always away from the equilibrium position. So displacement here, it's away from the equilibrium position. The other thing is, as we have seen, when the mass is away from the equilibrium position, there is always a restoring force trying to bring the mass to its equilibrium position. So you see here, the displacement is away from the equilibrium position and the restoring force towards the equilibrium position. The important thing here for simple harmonic motion, that the restoring force is directly proportional to the displacement, but in opposite direction. The math behind this is beyond of your syllabus, but this is what you have to know. The restoring force is toward the equilibrium position, the displacement is away from the equilibrium position, and they are directly proportional to each other. It means here, for example, it means when here the restoring force equal to 0. Why is this? Because we have here mg and we have the tension upward. They cancel each other, so the restoring force equal to 0. When the mass leaves the equilibrium position towards right or left, a restoring force will establish. It will increase till its maximum here. Again, I will repeat, the mathematics behind this is out of your syllabus. So going from the equilibrium position away will make the restoring force increase. So, but what will happen to the displacement? Also, it is increasing. Displacement here 0, it is increasing here till it is in the maximum value of it. That's why the force is directly proportional to the displacement. But the displacement has a direction away from the equilibrium position. Restoring force is towards the equilibrium position. That's why this minus sign is here. Restoring force is an opposite direction with the displacement. As we know that from Newton's second law, F equal to ma for a constant mass, F directly proportional to A, so we can write also the acceleration directly proportional to the displacement and in opposite direction. So this is very important for simple harmonic motion, for any oscillation to be simple harmonic motion. Now let's go to some important concepts here: amplitude, period, and frequency. The distance from the equilibrium position is called the displacement. We saw that. The distance from equilibrium position, here, it can be here, or here, or here, the distance is equilibrium. When the mass reaches here, so the maximum displacement called amplitude. So this is the maximum displacement from the equilibrium point. Of course, it's a vector directing away from the equilibrium point. Now we want to know the time period. We have to know first a complete oscillation. For a complete oscillation, for example, for a pendulum, if it's starting motion from here, this is only a quarter of the oscillation. This is when it's coming to the other point, it's half of the oscillation. It is 3/4 of the oscillation. Coming back to the same point, it's a full oscillation. So the time from here to here, it's T/4. The time, if the full time is T, time period. So this is from here to here, T/4. From the beginning till here, it's T/2. Coming to this point is 3/4T. Coming back, it is T. So this T is the time period, the time for one complete oscillation. It's not necessary for the oscillation to start from the maximum displacement, from right or left. It can be, for example, the oscillation can start from equilibrium position, so going to the maximum point to the right, then coming back here and going to the other side, coming back from the to the starting point. This is a full oscillation, and the time required for that is a time period. So to calculate the time period, if we have a number of oscillations, we have to divide the total time over the number of oscillation. This will give us the time for only one oscillation. This is the time period. The frequency F is number of oscillations per unit time. So we have to divide the number of oscillation over the total time. This will give us the number of oscillation per unit time. If we can see here that the time period is the reciprocal of the frequency. Yes, so time period is equal to 1/f, or F equal to 1/time, and the unit for the time period is second as SI unit. For the frequency, it will be 1/second, or we can write it second to the -1, and this is equal to hertz as a unit of frequency. Now, this is how to represent displacement, but with time graphically. The wave here, sinusoidal wave, so the function is sine function here. the amplitude is the maximum displacement from the equilibrium position. So if this is our equilibrium position, where is the y-axis is representing the displacement. These are all displacement here, but the maximum displacement is called the amplitude. This is the amplitude here. This is the amplitude. Here also we are getting the maximum displacement, which is amplitude. For the time period, okay, we have to see a complete oscillation from the crest to the crest here. It's completing one oscillation, so the time for that from here to here, it's one time period. Also, this is the time required from here to here is one time period. Also, this is from here to here is one time period. What about angular frequency? This is related to the frequency f by 2 pi f, and as we know, f is the reciprocal of t, so we can write it 1 over t. So this is how angular frequency related to t, and here it's related, it is related to f. What about the unit for omega? It is rad over second, so it is rad per second. Now here, from the displacement time graph, this is the displacement, the y-axis, and we have to be very careful about the units. This is in centimeter here, and this is the time in milliseconds. Determine the amplitude, the period, and the frequency of the oscillation. Now here we have the amplitude. We have to go to the y-axis. Where is the maximum displacement? This is the maximum displacement that we have. So our amplitude, which is x naught, equal to 10 centimeter, and we can write it 0.1 meter divided by 100. What about time period? It's time for one full oscillation. So from here till here, what is the time? It's 120 milliseconds. So the time period is 120 milliseconds, and we can write it 0.12 seconds divided by 1,000. What about frequency? Frequency is 1 over t, so it will be 1 over 0.12, which is equal to 8.33 hertz. Because we are here, f can be represented using hertz, which is 1 over second, which is the, so that's why here we have to use the unit of second. Now, phase and phase difference. The term phase describes the point that any oscillating mass has reached within the complete cycle or oscillation. So from here to here, it complete a quarter of the oscillation, so it is pi over 2 if we are going to compare it with circular motion. From here to here, it is quarter of a cycle with the angle of pi over 2. From the beginning to here, it's half a cycle with an angle of pi. So from the beginning to here, it's 3 over 4 of the cycle with an angle of 3 over 2 pi, 1/2. This is pi, this is 1/2 pi, and again we are back, so this is 2 pi a full cycle. So here we have 2 pi. This is half a cycle or oscillation, pi. This is half 2 pi, pi, half a pi, here 1.5 pi. The phase difference is the difference in phase angle between 2 sinusoids. We have here 2 oscillations. Now they have a phase difference of 1/4 of oscillation from here to here. This is 1/4 of the oscillation. In terms of angles, we can say that the phase difference is pi over 2. It is here very clear that a crest at a certain point is reaching a trough at the same point, the same time, so the phase angle between them is pi. So 1/2 of an oscillation is the difference. In terms of angles, the phase difference equal to pi. Here. This is the end of our lesson for today. Next lesson will be representing the equations, simple harmonic motion equations for displacement, velocity, acceleration with the graphical representations. Thank you.